have two excellent, very experienced speakers. They are geophysical experts, geology experts, and the title of this session is Geophysical-logging for Characterization of Bedrock Geothermal Bores. You guys are much more experienced than me. I'm hoping they explain some of what that means. And first up to do that, to introduce our speaker is a gentleman that I met in 2019 via Zoom, John Rhyner. He is another JR, John Rath, John Rhyner, and so we got confused a few times. But he's got 20 plus years experience with geography, geology, and geothermal. The meetings that I attended that John was in, I learned a lot about some of the mapping of New York City, which he was an integral part of. He's now located working with the EGG group in Florida, so he made a move down where it's warm. Will you please help me welcome John Rhyner?
Sound check. Hello, can you hear me? Okay, hi, I'm John Rhyner with NY-GEO, and this is a moment you've all been waiting for, the special introduction of our speaker. John, this is the only panel that has a special introduction, so I hope you're, yeah. But it is a special day, and NY-GEO asked me to do this because a couple of reasons. One is this is the inaugural time that the U.S. Geological Survey has been to an NY-GEO conference. That's right?
Your participants this first time.
Okay. Yes. So that's a big deal. USGS stands for U.S. Geological Survey. The second reason is because I have a personal connection and a professional connection with the USGS. I've been kind of a practicing geologist, hydrogeologist for 40 years. The first 15 years was in environmental consulting. The most recent 25 years was in geothermal, but there hasn't been really a week that has gone by that I haven't made use of a report or mapping or data that the U.S. Geological Survey has generated and issued and is readily available on the internet. So, you know, in my professional world, the USGS, I wouldn't be where I was if it weren't for the USGS and their tremendous information. You know, if you don't know anything about the USGS, it's Department of the Interior. It's part of the Department of the Interior. It's been around for well over 100 years, and the geologists and hydrologists and geoscientists have, you know, mapped every square inch of the geology and the mineral resources and the natural resources of the U.S., and they've even done a lot outside of the U.S. internationally. They've mapped the, you know, thermal resources, which, you know, our technology can tap into for direct heating and power production. They've characterized the U.S. for seismicity, you know, earthquake potential. So the work they've done has helped this country grow and economically, and as well as, you know, safety, being safe. And so that's a little intro about the USGS. I want to mention a couple other things. And the USGS, they rebranded themselves 20 years ago or so, Science for a Changing World. You know, it's not an academic exercise what they do, or it's been long viewed that way, but I've personally collaborated with the USGS on projects in my consulting business. My favorite project was the Cornell New York City Tech project. We teamed with the USGS. We got the project. Cornell liked the fact that we were teaming with a scientific federal agency, and they went with us. And that was with P.W. Grosser, my friends out there, and my former company, P.W. Grosser. So clients like to have sound science behind their decision-making to increase the confidence of the decisions we make, and not only in the geothermal industry. So I don't want to take up any more of John's time, but I've certainly made use of the USGS data and appreciated what they've done for many years. So John Williams is our presenter. He has his master's from Penn State, and he's with the USGS for 40 years, working through New York State, Pennsylvania. So let's have a warm welcome for John.
Hi. What? Okay, thank you very much for the kind words and the kind words for the agency that I work for. And more people hear those kind words. Hopefully, we'll be here for another 100 years. So we just started a project, a multi-year cooperative project with NYSERDA, and the primary objective of that project is to compile geologic, hydrologic, and geothermal information and put that information into a digital database, and then have that digital database or databases being served by an interactive web-based online mapper. We also have a secondary objective in that project, and that is to demonstrate the application of borehole geophysics in characterizing bedrock for geothermal applications. So this talk is part of that, getting the ball rolling in that, demonstrating the use of geophysical logging. Okay, so what are the objectives of the study or of the presentation? Provide an overview of the geophysical logging tools and methods applicable to the characterization of geothermal bores in bedrock. So this is there's whole courses in borehole geophysics, so you're going to get a very rapid overview of applicable methods in bedrock. And then we're going to present examples of geophysical log analysis and resulting information in multiple hydrogeologic settings. Okay, so what is a geophysical logging system? It consists of a spool, a drawworks or a winch of cable, and then that lowers and hopefully retrieves your probe as out of the hole. And then you have a whole series of different probes that are making geophysical measurements. And then you have the uphole component, which usually includes a computer to record and display in real time the data that you're collecting. So if you're out at the field demo yesterday, you saw our geophysical logger, which is essentially a self-contained logging system. This particular logging system did have 5,000 feet of cable, but I think it now has 4,000 feet of cable, and so that's the larger type of system that you can use, and the smaller goes all the way down to a suitcase logger that you can pick up and run on a battery. And then everything in between of the one shown here is what I think the manufacturer calls it portable, but it's a couple 100 pounds, so it's not that portable here. Okay, so one of the basic logs that we do, and this is a caliper log, and the caliper logs are essentially spring 3-arm spring loaded, and essentially you lower it down the hole, and then you bring it up, and those springs record the borehole diameter. And knowing the borehole diameter is very useful to delineate enlargements related to bit changes, washouts, and fractures. Useful for determining how much grout you might need, and then it's used in interpretation of many of the other geophysical logs. The The gamma ray log is the other go-to log for geophysical logging, and it basically is measuring gamma ray emissions, which are due to the presence of uranium, thorium, and daughter products of potassium-40. So gamma logs are very good for looking at clay content and mineralogy, and it has a good resolution of 1 to 2 feet, so you can delineate the various beds. It's very versatile that it can be run in air, water, or mud-filled, open PVC or steel-cased well. It is essentially used for lithologic identification and correlation. So we can look at some of the different signatures here. So if we have a very clean sandstone, very little clay, it's going to have a very low gamma response, along with a clean limestone, again, very low gamma response. And then you see that the shales have higher gamma response. Probably one of the highest ones that we see is from organic rich shales due to the concentration of uranium. So this was an example for like the Marcellus shale had significant uranium content. So gamma log, very good for looking at lithology and correlating between wells. Okay, so here's a gamma log from a gas well in the Ontario lowlands of New York State. So the gas well is penetrated Silurian shale, limestone, dolomite, and evaporites. So here's our gamma signature, and here's the interpretation. Basically, the high gamma response are shales, lowers are limestone in this case, and then more shales. Here's a limestone unit, more shale, and then limestone, and then down here is sandstone, and then here's a shaly sandstone. So has anybody got any guesses of what the different rock types that we've penetrated? They penetrated in this well. Does anybody know their Silurian stratigraphy? No. Everybody heard of Lockport dolomite? Yeah. So here's the stratigraphy. The top is the Vernon Shale, which is a very incompetent. Just was a well drilled in Syracuse in a geothermal well in which they had 200 feet of glacial deposits, and then they got into the Vernon Shale. And you think if you're in bedrock, you're home free, but no, there was 60 feet of essentially weathered clay that they had to go through. So a lot of casing in that. Okay, and then they got into a very competent. So the next is Lockport dolomite, and here Lockport dolomite is known for having hydrogen sulfide gas and something called black water, which is this really nasty corrosive water. Then we're into a thick sequence of shales, the Rochester shale, then the Irondequoit limestone, back into another shale, another limestone, and down here is the Medina sandstone, and the Medina was the target for this. So Medina is a commercial gas producing zone. So this is all within the first 800 feet. So a lot of lithologic variation, a lot of interesting properties of the different units. Okay, so I didn't talk about a density log. It's another nuclear log. I didn't talk about it because basically you need a radioactive source to do a density log. So it's really only done by the oil field. And so it's not part of a common suite that we'll probably be using in groundwater and in geothermal. But here, look at this very high density zone here. Does anybody have a guess what that zone might be? It's down in the Renales. This whole sequence is called the Clinton Group. There was iron ore mining done out of this unit up near the shores of Lake Ontario. So that is actually an iron ore that was mined in the late 1800s, in the late 1800s, and then the Mesabi range kind of took over because their iron ore was much thicker and much better. But they continued to mine it for red paint. So in upstate New York, many of the barns are painted with red paint, and it might be this from this unit. And so here's that unit, very, very distinctive, red color, oxidized, very iron rich, and quite dense. Okay, so the other types of logs are electric logs, and basically they're measuring the electrical properties of the formation. Single point resistance, it's a electrical resistance between a surface electrode buried in the mud pit or attached to a steel casing, and then the resistance down to a downhole electrode on the probe. So it's good for looking at clay content, porosity, and dissolved solids. So both clay content, it's going to affect. So clay would have very low electrical resistance, whereas sand would be have a higher resistance, but it's also affected by the dissolved solids in the formation. So it's resistance in ohms, not resistivity, which is in ohm meters, because the distance that's being measured over is changing as you lower the tool. So it's affected by borehole diameter, can be run in water or mud-filled open hole, and it has a very high resolution. So the well that was drilled yesterday essentially was such a low producer, there was virtually no water in the well, so we couldn't run the electrics. Okay, the normal resistivity log. So you have on the normal resistivity log, you have the electrode on right on the probe, and they're spaced at different distances, typically 16-inch and 64-inch. So the 64-inch will look deeper into the formation and less affected by the borehole fluid, as the 16-inch will be higher resolution but won't look as deep. So again, clay content, porosity, and dissolved solids. Water, mud-filled open holes, and you have long and short normal, 16 and 64 inches. Okay, in the oil industry, normal resistivity isn't being run anymore. They do electromagnetic induction log. The induction log has the advantage that it doesn't see the borehole fluid; it reads out into the formation, and it can be. So again, it's giving you a electrical conductivity or resistivity. So it's related to clay content, porosity, and dissolved solids. Very versatile air, water, and mud-filled open or PVC case, not affected by borehole fluid, and it's got high vertical resolution. So if we look at a resistivity log, be it done by a long, short, normal, or a EM induction log, we can see different properties, both of the fluids and the lithology. So here we've got we've got a shale, and it'll have a low resistivity. And then we get into a gas zone in a sandstone, it'll have a high resistivity. We hit oil, the resistivity is lowered, and then if you got salt water, it's even lower, very, very many times comparable to the shale. So yeah, here's the salt waters, another saltwater zone, and so on. So gamma is largely just affected by lithology, clay content, and the induction conductivity or resistivity is affected by clay content and the water quality. So we lay those two together and then shade in between, And what we see is if you have low salinity in the formation, the gamma log and the EM conductivity are going to track each other. And then if you get salinity, they're going to start to depart. So it's a very good way to, the combination of the two gives you a lot of information. This was from an oil well top hole in the Allegheny Plateau, which is sandstone and shale. Okay, the interpretation of gamma and resistivity logs in crystalline bedrock, like everything else in crystalline bedrock, is more complex and more difficult. But we can say some things that one of the things that very often stands out in the gneisses and the schist is the pegmatite zones, which are potassium feldspar zones. They're high gamma emitters, and then the basic rocks, the gabbros and the basalts, they have very, very low. So we can do some interpretation of the crystalline rocks with those along with a caliper. Okay, deviation log. I think this is probably of the most interest to this group because if you're drilling a borehole field at 20-foot centers, you don't want your boreholes colliding with each other. Probably the worst day in the drillers is start to see pieces of PVC pipe come up in your cuttings. So deviation logs measures the borehole azimuth and tilt, and that'll give you the drift of the borehole or the path of the borehole. And from that you can use to calculate the three-dimensional path of the borehole, and it's used to correct orientation of planar features identified on image logs, and it can be run in air, water, or mud-filled, PVC cased or open holes. The one we have that's commonly is a magnetometer, so you can't run it in steel. If you need to run it in steel, you need to go to a gyroscope, which is a much more expensive tool. So here's a pseudo 3D virtual 3D plot of the borehole path, and we can see that. So here's north, east, south, west, and here's the borehole path. So basically, it's going down for the first almost 200 feet. It's essentially vertical, and then it starts to veer off and keeps going down. And by the time it's down here, I think it was something like 50 feet off. I think it may be even more, 50 feet off center. So this was a deviation borehole in the Hudson Highland gneiss, and the metamorphic fabric was eastward dipping, and we'll see this relationship over and over again in metamorphic rocks between the borehole path and the fabric or foliation of the rock. So, and what is that? Well, there's no such thing as a vertical borehole, and what they tend to deviate up dip perpendicular to the bedrock fabric. So you're coming down vertical and you hit some sort of dipping fracture, it's going to tend to turn in there and become perpendicular. Okay, a borehole camera, a very fairly old technology. You've got fisheye view and sidewall in a typical. Typically, it's not oriented, so you can look at fracture dips, but to some degree, but you can't really get quantitative information. Very useful for direct viewing of lithology, bedding, foliation, fractures, and flow, and it can be done in water and air-filled holes, and it's affected by water clarity. So if you don't have clear water, you're not probably going to see much. The acoustic televiewer is developed by the oil industry, and now it's used in the groundwater and hopefully soon in the geothermal. And essentially, it's an ultrasound pulse echo system, and from it you get acoustic amplitude and transit time. And it's a oriented 360-degree acoustic image of the borehole wall. And that reflectivity and amplitude and transit time is all related to lithology, bedding, foliation, and fractures. And that it needs some sort of fluid, either water or light mud, that you can run in that acoustic televiewer. The most recent imaging tool is the optical televiewer. It's developed by the Japanese, and I guess the president of this company, Rayax, the guy was going on his daily commute, and he looked up at he was in the subway, and he looked up at the pole. The top of the pole had a very shiny connector that he could look at it, and he could start to see 360 degrees around. So he said, oh, that would make a great borehole tool. So that was invented of the BIPS, the borehole imaging processing system. So again, 360 degrees, optical image now, direct viewing of lithology, bedding, fractures, and foliation, water and air-filled holes. It's less affected by water quality than the fisheye because it doesn't have as far to see. But still, if you've got a muddy hole, a lot of turbidity, you're not going to see very much. Okay, here's some examples. This is from Indian Point Nuclear Power Plant. We're in the Hudson Highlands in the Inwood Marble. And so here's side-by-side acoustic and optical televiewers. And then in the middle, we've got some core in there to compare it. And so what we're able to see, we can see bedding fractures, and those are southeast dipping. And then we can see orthogonal fractures to the bedding northeast. And then we can see these subhorizontal fracture zones, which are very major water transmitters. And in this case, it's the inward marble, so that fracture zone has been solution enhanced. Okay, so we can take that. So it's 360 degree. So here's the unwrapped image. Of course, the Japanese did it. They broke it on the north rather than the south, which everybody else does it on the south. But anyway, so south, west, north, east, south again, and then we can wrap it back up and create a virtual core. Come on. Then we can spin that core, and essentially you've got a core. And this is from, I think it was Connecticut. It was at a landfill. I mean, you could almost reach out and touch those pieces of rock, and you can see all the staining and everything like that. After looking at how that rock looks like it's about ready to fall in that fracture zone. Okay, so as I said, both the acoustic and optical, 360 degrees. So if you have a planar structure like a fracture that's south dipping, it's going to show up as a amplitude curve. The low point is the dip direction, and then you can do with a little trig, the dip angle is going to be a tangent of the amplitude over the diameter of the borehole. And then, of course, then strike is 90 degrees to that. So here's an example of the first well we did before we even started the project with NYSERDA. This was we worked with Con Ed on this, and this was a 880 feet borehole in Yonkers. It was in the Manhattan schist or the Heartland schist, depending what geologist you believe. and it had a lot of banding in it. Then those were quartz host feldspathic, and you can see that they have a higher gamma signature. And this was very foliated. So with the software, we can pick out those foliations, pick the dip direction and the dip angle, and we can present them as either tadpoles. So here's 0 to 90 degree dip, and so this is dipping about, these are dipping about 60 degrees, and they're dipping in that direction, which would be into the northwest. And then we could also show them as sinusoidal waves. So we take all that data, and in a foliated rock, you got many planar features to map, and we plot them on a 2D. It's called a lower hemisphere stereonut plot. And so as the concept is, if you have a pencil, and just imagine a lower hemisphere right here. And so if you're perfectly horizontal, your plot right here, if it's dipping in that direction, you're going to plot over here. If you're dipping in that direction, it's going to plot over here. So that gives us the ability in a 2D plot to display a lot of these features on a 2D plot. And this is what it looks like. So here it is, a 2D plot, and these are all the the planar features, largely foliation planes that are plotted. So you're seeing, largely these features are dipping at about there 286 counts of those, and the average dip is 70 degrees. Okay, so we can look at different intervals, and we can just plot certain intervals. And this is a critical interval because I think this was a large interval from essentially 400 to 660. The foliations were at very similar angles, right? In other places, they were reversing. So this is the type of thing that can affect the deviation of the borehole. So the average dip was 62 degrees, and the azimuth was 295. And so if we plot those, we can see that they all cluster in this zone right here. So essentially, west, northwest, dipping at around 60 degrees. Okay, if we look at the borehole deviation, and we look at it on a bullseye plot, so here would be 0 point, and then we're going out to 50 feet. 50 feet, okay? So we can plot that with the deviation. We can plot the path of the borehole. So you can see I've plotted the path of the borehole is in the southeast direction, again perpendicular to the foliation. And then we've got numbers here, and these are at the depth. So you can see the first 500 feet, the borehole is within 10 feet of vertical, and by the time you get down to 880 feet, you're over 50 feet away from the origin. So we can put that into a 3D plot. So here it is again. We've got essentially vertical down to about 400 feet or so, and then it starts to wander off in this direction, and that's the exact direction or interval in which we have a very consistent foliation that's controlling this deviation. Then we can also show it on on the map. So here's the top of the hole, and here's the bottom of the hole, 50 some feet away. So this may be an issue if you're trying to put 50 boreholes in this space, right? Okay, so does that happen in other boreholes? Yes. We've logged probably 30 boreholes with a complete suite along the water tunnel in Manhattan, and these boreholes are 600 feet deep. You can see some of the superficial mapping with the angle and the dip direction of these foliations here. So about 70 degrees, so consistent with what we saw up in Yonkers. And so here are the plots. So this is the plot of the foliation that we've been looking at, mostly westward dipping. And then here's the path of all these boreholes. And I think they're up to, I don't know, 50 or 60 or 70 feet at the bottom of the hole. So this is a very consistent thing that happens in drilling in these metamorphic rocks with fabric. It'll also happen if you've got sedimentary rocks that are dipping. If you've got horizontal rocks, you probably have a much better luck in drilling a vertical borehole. Okay, so in addition, we also look at the fluid properties and the permeability of the rock as well when we log these wells. So if you have a deep borehole, they'll typically penetrate multiple flow zones, fracture zones at a different hydraulic head. So if they're different, then you'll get vertical flow going on in the borehole from zones of higher head to zones of lower head. So we run flow and fluid property logs collected under both ambient conditions to determine the direction or rate of flow between producing zone. And here's a couple cartoons. You can see upflow and downflow in different wells. Okay, and we measure the flow either with a spinner flow meter, which is just a spinner, or a heat pulse flow meter. The heat pulse flow meter is a very low velocity, high resolution tool. And then we also have an electromagnetic flow meter as well, which is quite versatile and can measure a wide range of flows. And it also has built into it a fluid resistivity and temperature, which is really kind of cool because then we don't have to do another run. It's part of the probe when we get that information along with the flow. Okay, then we also do a pump flow, and we repeat the flow and the fluid property logs. We'll put a pump up in the casing and pump it at a relatively low rate, and then repeat all our measurements down here, as well as fluid and fluid property wells. We can then take that data and so we have a pump flow rate, a pumping rate, drawdown. We can analyze using a program called Flash, which is flow log analysis for single holes, and we can estimate flow zone, transmissivity, and hydraulic head of each one of those zones. So if anybody's done a packer test, that can be very laborious. In this case, we can get very similar information. We don't have we have good resolution, but we can't get the really low transmissivity zones. But I would think those are of interest in the contamination field, but not as interested. I would think of the geothermal. You're really looking for the players, and this will identify those zones and tell you what the hydraulic head is and the transmissivity. Okay, here's an example from way long ago when I was just starting with the survey. This is down in Pennsylvania. We had a borehole put in for a development, and that borehole flowed at 75 gallons per minute. So the setting was in an upland draw, and it was on the side of a anticlinal hill. The beds here are sedimentary beds, and here's the strike, and here's the dip, so 35 degree. So this is the hole that flowed at 75 degree, 75 gallons per minute. Here's the fracture down here at 260 feet or so, and this is the temperature log. You can see the nice break associated with that upflow. Probably is some additional flow coming in here as well because of the change. We didn't have a flow meter at the time. We did something called brine tracing, which doesn't have the resolution, but it was enough to say, yeah, virtually all the flow is coming out of this zone right here. And what was really interesting is that we monitored the water levels in two wells, two domestic wells. One was downslope, down dip, here about, I think 50 feet away or so. And then this well was 200 feet away. We saw no effect when we let the well flow for several hours. This well sucked right down 30 feet of drawdown in this guy's a well. So this all was able, even though we didn't have the imaging, we could surmise that this was some sort of bedding plane connection in which the up dip it would shallow. So this zone was on the up dip side and it hit shallow, and then this zone that they wouldn't have even reached it being down dip.
Excuse me, John.
Yeah.
But sending that warning and then with that.
Okay. So I'm gonna move. So here's a recent geothermal well for DOE. It's their demonstration project in West Point, and this well hit at 200, close to 300 feet. Here's the subhorizontal fracture. It hit at 297 feet, and here's the flow meter. And this thing flowed when they logged it 30 gallons per minute artesian flow. And here's that flow coming out of that well. When they first, it was about 50 to 100 gallons per minute when they first did it. And then later on, 3 hours later, they were logging it, and it had settled down to 30 gallons per minute. This was supposed to be they were supposed to instrument this with thermal sensors, but they ended up grouting it and having to abandon it. They drilled another well on the other side of the West Point property, and they've got virtually no flow in that well, and they instrumented that, such as fractured rock. Okay, we had during the whole Marcellus boom, there were some core holes put in, 1,500 feet deep that we logged. We did a complete suite of logs in that. And this particular log had about, I think, eight gallons per minute or so of downflow. It also had saline water, and it had gas as well, so it had it all. And so here's the cascading water coming in. You can see the subhorizontal fractures and that water, pinhole squirts into it. And obviously there was additional water. So this is about this water and the water down below. You can see that fracture as well as about 8 gallons per minute going down that hole. And so now we're down at 660 feet, and we've got some iron flock in this well, which was not good, but it really showed you where that water was going out. So you can see that water being sucked out at that low head sound at 660. And then we went deeper, 900 feet, subhorizontal zone, fracture zone. And you can see that water coming in is saline water. And it's going down the borehole because it's more dense, right? It's funny, the guy that was logging this says, I saw frac fluid, I saw frac fluid. No, it turned out we sampled it and it was just natural saline water down at 915 feet. Okay, here's another example, geothermal in the Allegheny Plateau. They had saline water and gas in the well, and we were able to trace the horizontal fracture zone across the borehole well field, which was 300. The driller got rid of the water. He contained it because it was saline water, and then he injected it back in, and we monitored. Here's the effect of it, that injection so we were injecting in K9 and measuring in A9 a couple hundred feet away, and you can see that build up, and then it dissipates. So that was a good way to handle that saline water. So the methane gas, about half the wells actually unloaded. The methane gas just unloads the water column. This particular well discharged about 100 gallons per minute of saline water for 15 minutes. Incidentally, this guy burned his rig on the first well that he drilled. So you can see he's got that methane and water at least a little bit away from his rig. Okay, so here's another one of the wells at the same site. Is it going to run? Okay, that one isn't going to run, but basically it was spurting out. So you don't have to go out to central New York to find gas. This is a call we just recently got from a residential homeowner who their well just started unloading on them. And we can see, look at that. So you can see the vegetation kind of moving a little bit, and that's methane coming out. And then go back on. There you go. So that's all unloading from gas. And what's interesting, usually the gas, will dissipate. This actually, they knew they had gas, but it just 10 months ago, it started unloading like that. So what caused that? Well, the only thing we could think of is about 10 months ago, there was the Ramapo fault, and we see it in our observation well, so maybe something had taken on. Okay. Okay, so here are the questions. Probably be more productive if you just had any questions, but if you look at these and we could discuss these now or over a beer. I want to highlight one thing. Precursor to our project with NYSERDA is we wrote a short little report entitled Hydrologic Framework and Considerations for Drilling and Grouting of Closed-Loop Geothermal Boreholes in the Erie, Ontario Lowlands, and Allegheny Plateau of New York State. So we'll put some of these out, and it's a QR code you can scan, and that's online. It's hot off the presses, which I don't know if that's appropriate if it's online only, but it's hot off the presses.
Okay, great. Thank you, John. So if folks in the audience don't have questions, then we'll default to your questions, but let's open it up and see if anybody wants to ask any questions.
People.
Hang on just a second, because we're going to try to get your voice on the record, and if you identify who you are and your organization.
Hi, my name is Brendan Wyden. I'm with a little outfit called the Narrowsburg Union. How does the temperature, the Earth's temperature, vary as you go down? Because I saw that once it looked like it was changing. There was kind of a 45, more or less straight, a couple wiggles, and then a 45 degree. Was that getting colder or warmer?
Yeah, so that was plotted, increasing temperature to the right.
Increasing temperature.
Right. So if you look at the geothermal, the temperature in a borehole, there's an upper zone that essentially fluctuates with time.
Around what? In what range?
It all depends. It's totally dependent how fractured it is. You know, what's the range?
I think like people talk about 50 degrees. The middle of New York State. You're talking.
And then you see it start to come around, and then it bends. And if there's no flow going on in the borehole, that temperature gradient will approach the geothermal gradient of about 1 degree per 100 feet. So yeah, depending on where you are. Now, if there's borehole flow in the well, like we showed that one artesian well, essentially you're going to have that warmer water at depth coming up the borehole, has no time to equilibrate, and you're going to get isothermal gradient. So that's why the temperatures is so great for looking at where the fracture zones are. But that's not a good temperature that you want as a geothermal. It needs to be grounded in, and you need to be in equilibrium, and that's when you do your thermal conductivity tests.
So the difference between a 250-foot deep well and a 500-foot deep well, is it safe to say a 500-foot deep well is always going to be colder?
No, warmer. Geothermal gradient, 1 degree per 100 feet. Once you get below that active circulation, yep. So if the active circulation, and I looked at different lithologies, different topographies, a sandstone versus a shale and with not a lot of topography is going to go geothermal much sooner than a porous sand or a limestone, porous limestone. So that may occur at 300 feet, and then from 300 to 500 feet, it's going to go 1 degree per 100 feet.
So a second question, if I can. Sometimes we think about the Earth as being like a battery, like an electrical battery, and that if we draw down the battery, if it's wintertime, we're taking heat out of the Earth, at some point it will lose its heat delivery content, and we're not going to be able to get much more heat out of it. And is that, if you have, is a strategy when you have that to have multiple boreholes, have one field that you draw early in the season, and then you have another one that you do later in the season, kind of like it's a virgin field, virgin heat, or to what degree does it all evens up? Right.
So there's open loops and closed loops.
Yeah.
In an open loop, you definitely want to have, an injection, a pumping and injection, and then reverse them.
Yeah.
In a closed loop, almost all in all cases they're using the same borehole, and I think that's a good point of research is how many boreholes you need when you start to lose that effectiveness. If you particularly probably, depending on your climate, depending on your use, if you're heating positive or cooling, you definitely can change the thermal regime, and it could become less efficient.
Well, how long does it take the Earth to come back to equilibrium?
Yeah. Yeah.
That's 1,000 years.
So if you've got a lot of groundwater flow, high permeability, high transmissivity, that cold water or warm water is going to be gone. If you got a shale with no fractures, it could take a long time. Yep.
Mark Bagdon, LaBelle Associates. The wells that you drilled, the test wells that had artesian flow or downflow, are they grouted after you're done to stop the flow? I mean, is there any potential hazard to impacting groundwater wells in the area or contaminating clean water with saline water? I mean, what?
Certainly. Yeah, you bring saline water up into the shallow freshwater zone, that's definitely a problem. If you've got fresh water going down, you're draining the aquifer, or if you've got shallow contamination, but you got deep. So yeah, any open borehole is a potential pathway that disrupts the natural system. And so in geothermal closed loop, you are grouting those, and hopefully your grout is sealing off, and it becomes a no issue. In closed loop, you have, any open borehole. Got to think though, we've got all these domestic wells out there they grout to competent rock, and they're open hole. So there's water going up and down these wells, and there is definitely the potential for cross-contamination. Yep.
Thanks for the talk. Marshall Pontrelli with McPhail Associates. Are there any geophysical tools that give decent mineralogical content that could be used to correlate to things like, well, specifically thermal conductivity? Silica content, for example?
Yeah, so largely just say a gamma log is going to tell you how much shale versus sandstone is. So, but there are there's something called a gamma spectral that actually breaks it down to uranium, thorium, and potassium-40. In the oil industry, there are actually mineralogical logs. We don't have access to them, but it would be very interested. What you really want is a thermal conductivity log. Yep. And unfortunately, we don't have that. The problem is, if you've got an open borehole, that's not particularly representative, because you could have this borehole flow going on. Yeah. I think we need to log more wells with these tools, compare them to the tests that are being done, and see what we can come up with. Yep.
Oh, okay.
Oh, I should say on that West Point one, they actually grouted in temperature sensors all the way down, so they're going to get good transient temperature data. So that'll be very interesting results. Unfortunately, that other well, they had to grout shot. Yep.
Yeah, hi. My name is James Morier. I'm with the New York State Department of Environmental Conservation. When we do our geothermal systems, we try to balance out the heating and the cooling loads so that you don't lose your well or your field over time. Yep. How can you determine if that's really necessary, or if you have enough groundwater movement so that you don't have to worry about that? Because many of our facilities, especially in the North Country, are extremely heating dominant.
Yeah. So I think that's where doing the flow testing and estimating the transmissivity is going to give you some indication of potentially what the groundwater flow is going to be able to take that heat away from it. Again, this is it's all new ground for us. We were more interested in, okay, this is transmissivity, this is where the contamination is, or this is what do you want to put the water supply. Now we're talking about heat. So, but it's really an exciting field for us now, and those are really good questions. Yep.
Just want to give John a round of applause. I mean, now these were all good questions. I had my own answers for all of them, and I could talk for an hour on each of those questions. But you saw a lot of slides. A lot of that is really relevant to open loop type systems or standing column wells, which I've got a lot of experience with in New York City, again with P.W. Grosser. We did St. Patrick's Cathedral, and those drift measurements that John was talking about came in handy because we did see this pattern throughout New York City. So when we planned for St. Patrick's Cathedral, we expected the drift, and we saw it. To the point of we started the holes pointing in the opposite direction to see if we could like make up, but they still eventually came back around. And the big issue with the drift is, what are the DEC requirements going to be for drift monitoring? I mean, I think we got a waiver now to 1,000 feet drilling without going through the DMN requirements, but drift monitoring, I assume, in some level is still going to be required. So, and especially in New York City area, if you know the drift, you don't have a lot of room to drift for a 1,000-foot hole. So, I mean, we could talk about it for a long time. But one last thing is, geologists are very important. You know, ASHRAE, National Groundwater Association, and IGSHPA, they all recommend that you have a geologist on your team. I mean, half the cost of a geothermal system is the bore field. So it makes sense that you have, like, the Earth is not a black box. That's what I always say. So it makes sense that you have an experienced geologist working with you. It may not seem like that a lot of that information was helpful, but it is for an open loop system. Closed loop system, certainly drift monitoring, and that's where a geologist can help out. So thank you again, John.